Hello everyone, my name is Dr. Vile. Welcome to my A-Level Chemistry YouTube channel. The aim of these videos is to help prepare you for your exams in chemistry, and this particular video is going to focus on the ideal gas equation, PV equals nRT, and then we'll also look at the combined gas laws as well. And we'll take them one at a time, and we'll look at plenty of past paper questions to help practice these skills. What is the equation? What do the terms mean? So firstly, you've got the equation, which is P times V, that's a little times sign, equals N times R times T. So let's look at what each of the terms mean. P is pressure. And for this equation, you've got to make sure that you use the appropriate units. Now, pressure needs to be in pascals. And we'll look at different conversions there. So you've got to convert your pressure into pascals first. Make sure to use your data sheet on the back of the exam paper that will help you with this. V is your volume. And your volume needs to be in cubic meters. Now, that's not the normal unit for volume, so you're going to have to play around and convert there. Remember to use your data sheet. N is simply the number of moles. That's easy enough. R is your gas constant, which is given to you on your data sheet, so just look that up. And T is your temperature, and the trick here is that you're going to have to convert into Kelvin. And remember, you have to add 273 to go from degrees Celsius to Kelvin. So there's the equation. P, pressure, times V, volume, equals number of moles, N, times R, the gas constant, times T, the temperature in Kelvin. On the next slide, I'm going to talk you through how we rearrange this. So P times V equals nRT. And a very typical scenario would be that you might need to calculate pressure, for instance. So if this is our base equation, let's work for all the possibilities. Say you need to calculate the pressure on its own. Well, what you need to do is divide both sides of the equation by V. So that would be N times R times T divided by V. Or let's say you needed to calculate V. You would divide both sides by P, because P over P just makes the term disappear from this side because it just equals 1. So V would be N times R times T divided by P. And then there are two more scenarios you might encounter. One where you want to calculate N, to make N the subject of the equation. So you could say here that you need to divide both sides of the equations by R times T. So R times T divided by R times T just disappears. And then it becomes N equals P times V over R times T. And then the other scenario that you might encounter is temperature. Well, here you divide both sides of the equation by N times R, so you'd end up with P times V over N times R. So it's really important that you not only know the equation, but you're confident in how to rearrange it. So let's look at some examples how to use this based on past papers. So this question says, calculate the volume in centimeters cubed that 2.54 times 10 to the minus 3 moles of nitrogen occupies at a temperature of 120 degrees Celsius, pressure of 101 kilopascals. So we know firstly that P times V equals N times R times T. The aim of this question is going to be to calculate the volume. So we can then say that volume equals number of moles times R times T divided by P. Now at this stage we're going to have to plug the numbers in from the question, but making sure to convert the units appropriately. So the number of moles is 2.54 times 10 to the minus 3. We don't need to do anything with that, that's good news. And then we're going to times that by R, which is your gas constant, which is just 8.31 on the WJC datasheet. And then temperature. Now temperature is 120 degrees Celsius, so you're going to have to do 120 plus 273. So that's 393 Kelvin. And then we're going to divide by pressure. Now the pressure is 101 kilopascals, which is 101 times 10 to the power of 3, we times it by 1,000 pascals. And you chuck all that into your calculator and it'll give you the answer in meters cubed. And it comes out as 8.21 times 10 to the minus 5 meters cubed. I've left the number in the calculator. Now we need to convert that into centimeters cubed. That's the aim of the question. So we have to times this by 1,000,000. There are 1,000,000 centimeters cubed in a meters cubed. So you times it by 1,000,000, or 1 times 10 to the power of 6. And that is the same as 82.1 centimeters cubed. So a different question altogether. Another experiment, you've got 160 centimeters cubed of hydrogen is formed at 20 degrees, a pressure of 1.01 times 10 to the power of 5 pascals. Assuming that hydrogen behaves as an ideal gas, calculate the number of moles of hydrogen formed. So it's a completely different question. Start off by writing out the ideal gas equation. You never know, you might get a mark just for writing out the equation. And then we're going to rearrange to make N the subject. So N equals P times V divided by R times T. And then we're going to plug the numbers in. So the pressure is already in pascals, so we don't need to do anything with that other than plug it in. That's good news. The volume is 160 centimeters cubed. Now, it needs to be in meters cubed, so we're going to divide 160 by 1,000,000. Which comes out as 1.6 times 10 to the minus 4, because it needs to be in meters cubed. These conversions are on your data sheet, so do check that if you're not sure. R is just the gas constant, which is 8.31. And then the temperature is 20 degrees. We have to add 273. So that's 293. And you chuck all of that into your calculator. And that comes out as 6.64 times 10 to the minus 3 moles, and that's the answer. So in terms of the marks there, I guess there'd be 1 mark for rearranging the ideal gas equation, 1 mark for converting all the units appropriately, and then the final mark for getting through to the right answer, plugging them into your calculator appropriately. Okay, so we're going to move on to a combined gas law now. Now this is where you take a gas and you do something like change the temperature, or you change the pressure, and you see how it affects one of the other properties. Now the equation is written like this, so you've got P1 times V1 over T1 is equal to P2 times V2 over T2. And we're going to see how we can use this to solve problems. The general principle is when you increase the temperature of a gas, it'll expand, assuming other things are constant, so the volume would increase, and things like that. So we're looking at what one of these will have an effect on the other. So if we change the temperature, how does that change the volume? If we change the pressure, how does that change the volume, and so on. Look at a question. On adding a strip of magnesium to hydrochloric acid, 125 centimeters cubed of hydrogen gas formed at 24 degrees, pressure 1.01 times 10 to the power of 5 pascals. Calculate the volume by this gas under the same pressure and at a temperature of 52 degrees Celsius. So we know that P1 times V1 over T1 equals P2 times V2 over T2. So this is the new temperature, the new pressure, and the new volume. Now it tells you that it is the same pressure. So P1 and P2 are the same. Therefore, we can take them out of our equation, and we can actually just say that V1 over T1 equals V2 over T2. And the aim is to find the volume, which is V2. So we can write this out as V2 equals, now we're dividing by T2 here, we want to make it on its own. So what we're going to do is times both sides of the equation by T2. So V2 is equal to V1 times T2 divided by T1. And then we'll start plugging the numbers in. Now, I've told you in the previous slides that volume should be in meters cubed. However, for the purposes of this question, we can leave it in centimeters cubed, and it just means our answer will come out in centimeters cubed. So I'm going to stick with 125. We do still have to convert the temperature into Kelvin because it's got a non-linear conversion system. So T2 is 52 plus 273. So that's 325. And then we divide by T1, which was 24 degrees, plus the 273 is 297. And you chuck all that into your calculator. And the new volume is 137 centimeters cubed. And let's see if this makes sense. We've increased the temperature from 24 degrees to 52 degrees. So by increasing the temperature, the volume of the gas should increase at a higher temperature, and it's gone from 125 to 137, which makes perfect sense. So that is good news. And let's look at one more example to finish. Here we've got a question about something called a hydrazine. We don't really care too much about what that is for the purposes of the calculation. It says 0.16 grams of hydrazine at 398 Kelvin and 1 atmosphere pressure had a volume of 163 centimeters cubed. Calculate its volume at 273 Kelvin and 1 atmosphere pressure, and hence show that its molecular formula is N2H4. Okay, so we know P1 times V1 over T1 equals P2 times V2 over T2. And we also know that the pressure is staying constant at 1 atmosphere. So we can say that V1 over T1 equals V2 over T2. So what we're going to try and calculate is V2, same as we did on the previous bits. We can say that V2 equals V1 times T2 over T1. Plug some numbers in now. The original volume was 163 centimeters cubed. Once again, I'm going to leave it in centimeters cubed, just for now. And T2, the new temperature, is 273. And T1, the original temperature, was 398. So I'm expecting the volume to decrease because we're cooling the hydrazine down from 398 Kelvin to 273 Kelvin. Yeah, and it's come down to three significant figures to be 112 centimeters cubed, which makes good sense. So that's the answer to the first bit. I'm just going to put this in a box so it doesn't get muddled now with the rest of it. We now need to show that its molecular formula is consistent with N2H4. So we'll write out our ideal gas equation, PV equals nRT. And we know the mass of the hydrazine, and we want to calculate the number of moles, and therefore we can work out the molecular mass and then see if that makes sense with N2H4. So we're going to say that N equals PV over RT. Now the pressure is 1 atmosphere. Now that is 1.01 times 10 to the power of 5 pascals. You can just get that on your data sheet. I'm not super clever, you just look it up on your data sheet. The volume we've just calculated is 112 centimeters cubed. The gas constant is 8.31. And I've just realized I'm making a mistake here. When I use this equation, I don't want to use 112. I need to use it in meters cubed. So I'm going to divide by 1,000,000. So that's 1.12 times 10 to the minus 4, because it needs to be in meters cubed for this bit. And then divide by 8.31 times by the temperature, which was 273. And that comes out as 4.99 times 10 to the minus 3 moles. And we know that N, which is the number of moles, equals mass divided by molecular mass, mR. So molecular mass, mR, equals mass divided by moles. So that's 0.16 divided by this 4.99 times 10 to the minus 3. Which gives me an answer of the molecular mass mR equals 32, which is consistent with N2H4, where nitrogen is 14, 2 of those makes 28, plus the 4 gives you 32. So I'm happy with this. My calculation is correct. Anyway, thank you for watching this video. It was a bit longer than I planned it to be, but I hope it was helpful in terms of understanding the ideal gas equation and the gas laws. If you found this video helpful, please like it, please share it with your friends, please subscribe to the channel, and I'll see you next time. Thanks everyone.